Somewhere beneath the islands of the Philippines, a crack in the earth more than 1,500 kilometers long has just shifted again, and the scientists who study it are not watching for the next headline. They are watching one single number, not a magnitude, not a death toll. A quiet measurement tracked year after year by GPS stations bolted into solid rock that tells them exactly how much stress is building up before the ground finally gives way. If that number keeps climbing in the wrong place, it could be the difference between a minor tremor and a catastrophe that reshapes an entire region. And right now, in more than one segment of this fault, that number is climbing steadily, in full view of the researchers tracking it, yet largely invisible to everyone else. Let's start with what this fault actually is, because most people outside the Philippines have never heard of it, despite it being one of the most dangerous structures on the entire planet. The Philippine Fault is a massive strike-slip fault, meaning two enormous blocks of the Earth's crust are grinding sideways past each other rather than colliding head-on. It runs the full length of the archipelago, from the northern tip of Luzon Island, home to the capital city of Manila, all the way down through the central Visayan Islands and into Mindanao in the south. In terms of scale and danger, geologists directly compare it to the San Andreas Fault in California, the North Anatolian Fault in Turkey, and the Saging Fault in Myanmar, the exact structure. Responsible for the devastating magnitude 7.7 earthquake that killed thousands of people in March of 2025. All of these faults share the same terrifying trait. They cut directly through major population centers. Here is where the one number becomes so important. Scientists studying the Philippine Fault use GPS and satellite radar to measure something called the slip rate, essentially how many millimeters the two sides of the fault are sliding past each other every single year. Along different segments of the fault, that number ranges from about 10 millimeters a year in the south up to roughly 35 millimeters a year in the central and northern sections. That might sound tiny, almost meaningless, but multiply a steady creeping motion like that across decades and even centuries, and you start to understand how enormous earthquakes get built 1 millimeter at a time. But here is the twist that keeps seismologists up at night. Not every part of the fault slides smoothly. Some sections genuinely creep, releasing that built-up stress gradually and relatively safely. Other sections are what scientists call locked, meaning the two sides are essentially jammed together, unable to move at all, even as the deeper crust beneath them keeps trying to slide. When a section is locked, it does not mean the stress goes away. It means the stress keeps accumulating silently year after year, like a rubber band being stretched tighter and tighter, until the rock finally cannot hold any longer and it snaps all at once in a single violent earthquake. This is exactly the situation researchers have flagged for a stretch of the fault called the Infanta segment, which lies dangerously close to Metro Manila, a metropolitan area packed with more than 10 million people. Scientific modeling of stress transfer along the fault shows that this particular segment has already absorbed significant pressure from two previous massive earthquakes. The magnitude 7.5 event back in 1973 and a magnitude 7.7 event in 1990. Both of those historic ruptures effectively pushed additional stress onto the Infanta segment without releasing it. That segment now sits roughly 60 kilometers from Manila, quietly locked, quietly loading, while thousands of buildings and millions of lives sit directly in its potential path. By the way, if this kind of science actually fascinates you, now is a great time to like and subscribe, because we dig into exactly this kind of hidden geological risk every single week, long before it becomes a breaking news headline. Now let's talk about what actually just happened, because this is not a hypothetical scenario dreamed up for a video script. In June of this year, a massive magnitude 7.8 earthquake tore through the southern Philippines near Sarangani province on the island of Mindanao, the strongest earthquake to strike the country in roughly 50 years. It killed dozens of people and caused widespread destruction in General Santos City, collapsing buildings and leaving lasting damage across the region. That earthquake did not occur directly on the Philippine Fault itself. It struck along a nearby subduction zone called the Cotabato Trench, where one tectonic plate is diving underneath another. But here is the part that should genuinely concern anyone paying attention. Scientists who modeled the stress changes from that massive earthquake found that it likely transferred additional pressure onto the neighboring Philippine Fault and onto an unruptured 100-kilometer stretch of the Cotabato Trench itself, effectively loading these nearby structures one step closer to their own breaking point. This is how earthquake systems actually behave in the real world, and it is very different from how most people imagine them. A major quake does not simply relieve pressure and leave everything else calmer. It often redistributes that pressure onto neighboring faults, sometimes bringing them significantly closer to failure, and sometimes doing so quietly enough that the connection only becomes clear years or even decades later. Researchers studying this exact region have documented this pattern repeatedly. Across the past century, The 1973 Rage Gulf earthquake appears to have loaded stress onto Masbate Island, which then ruptured in moderate earthquakes decades later, in 2003, 2020, and again in 2023. The 1990 magnitude 7.7 earthquake in northern Luzon appears to have set the stage for two additional major earthquakes that struck the exact same region 32 years later, in 2022. History along this fault does not move in isolated, random events. It moves in chains, one link quietly setting the stage for the next. So, what is the actual number scientists are watching right now, in the simplest possible terms? It comes down to accumulated slip deficit, essentially the total amount of movement a locked fault segment owes the surrounding crust after years or decades of remaining stuck in place. Along the unruptured stretch of the Cotabato Trench near this year's devastating earthquake, researchers estimate that roughly 2 meters of slip has already silently accumulated, energy that has nowhere to go except into a future earthquake potentially as large as magnitude 7.6 to 7.8. That is not a distant, abstract possibility. That is a specific, calculated number, sitting there, waiting. It is worth being clear about what this number can and cannot tell us. It cannot predict an exact date. Earthquake science, even with satellite precision and decades of GPS data, still cannot reliably forecast that a specific quake will strike on a specific day, no matter how confidently some corners of the internet might claim otherwise. What this number can do is something arguably more useful for everyday people. It identifies which sections of a massive, complicated fault system are quietly becoming more dangerous over time, allowing scientists, city planners, and emergency management officials to prioritize exactly where stronger building codes, better public education, and faster emergency response planning matter most. This is also why researchers studying this region keep repeating a specific warning, almost word for word, no matter which segment of the fault they happen to be analyzing. A quiet fault segment is not automatically a safe one. In fact, some of the most dangerous segments are the quiet ones, precisely because their silence means they have not released their stored energy in a very long time. Scientists studying the southern segment of the Philippine Fault near Agusan del Norte and another section on southern Leyte Island have both pointed out that these particular stretches have not produced a major earthquake in at least 50 years, even as the surrounding crust continues its steady, relentless millimeter by millimeter slide. It helps to understand how scientists actually arrive at this one number, because the process itself is a genuine feat of patient, careful observation stretched across years and sometimes decades. Networks of GPS stations, some of them continuously recording for decades, sit fixed to bedrock across the islands, tracking their position down to a matter of millimeters. When researchers compare those positions year over year, they can literally watch the ground creep, some stations drifting steadily in one direction relative to their neighbors across the fault line. In more recent years, satellite radar interferometry, a technique that compares radar images of the ground surface taken months or years apart, has added another layer of precision, allowing scientists to detect creep and strain accumulation across entire fault segments rather than just at individual GPS points. Together, these tools have turned what used to be an educated guess into something closer to genuine measurement. This combination of GPS and satellite radar is exactly how researchers identified the creeping sections of the Philippine Fault on islands like Leyte and Masbate, where the ground moves smoothly and steadily at rates between roughly 23 and 36 millimeters per year. It is also how they identified the much more concerning locked sections, where that same steady motion simply stops at the surface, even though the deeper crust keeps pulling. That contrast, smooth motion on one side and total silence on the other, is precisely the kind of signal that tells scientists where stress is quietly stacking up instead of being safely released. There's also a historical pattern worth understanding, because it explains why researchers take these locked segments so seriously instead of dismissing them as background noise. Detailed analysis of earthquake records stretching back more than 50 years shows that the Philippine Fault system has generated over 60 earthquakes of magnitude 5 or greater, averaging out to roughly one significant earthquake every single year somewhere along its length. Of those, around 10 have been genuinely destructive, translating to a major, damaging earthquake striking somewhere on this fault system on average once every 5 years. That frequency alone should be sobering, but it becomes even more significant when you realize that certain specific segments, the locked ones sitting closest to major cities, have gone conspicuously quiet for far longer than that average would predict. This kind of research does not exist purely for academic curiosity. It directly shapes how governments and communities prepare for what eventually comes, Population centers sitting along segments that models flag as increasingly loaded are encouraged to strengthen building codes, retrofit older structures, and rehearse evacuation and emergency response plans well before any warning ever arrives, since a locked fault segment gives no dramatic signal in the days or weeks before it finally ruptures. For residents living anywhere near the Philippine Fault or the surrounding subduction trenches, the practical takeaway is straightforward. Know your evacuation routes, keep emergency supplies on hand year-round, and treat earthquake preparedness as an ongoing habit rather than a reaction to the latest headline, because by the time a major quake makes international news, the moment for calm, unhurried preparation has already passed. Here is the honest, sobering bottom line. The Philippine Fault, alongside the network of subduction trenches surrounding it, has produced more large earthquakes over the past decade than almost any comparable region on the planet, including well-known earthquake country like Southern California. This year's devastating magnitude 7.8 earthquake was not an isolated freak event. It was the latest entry in a long, interconnected chain of stress being built, transferred, and occasionally released across one of the most tectonically active regions on Earth. Researchers have documented similar clustering repeatedly throughout the past century, groups of earthquakes striking the same general region within months or a few years of each other, almost as if the crust is working through a backlog of accumulated stress in bursts rather than releasing it evenly over time. And right now, quietly, invisibly, the number scientists are watching on more than one section of that fault continues to climb. If you found this breakdown genuinely eye-opening, make sure to like this video and subscribe, because we will keep tracking this exact fault system and translating the science into something everyone can actually understand and prepare for. Stay curious, stay informed, and remember that the ground beneath our feet is moving far more than most of us ever stop to think about.